Dr. M.A. Bhagaveni, Professor, Department of Electronics and Communication Engineering, College of Engineering Gindi, Anna University, Chennai. Dr. M.A. Bhagaveni graduated from Government College of Technology, Coimbatore, has completed her Masters and PhD at College of Engineering Gindi, Anna University. Her field of interest includes cognitive radio, ad hoc networks, wireless sensor networks, and wireless communication. She has completed 2 projects, one for CVRDE and the other for DST. She is the recipient of Young Scientist Award from DST. She has got 2 Best Research Paper awards in international conferences. She has published more than 70 research papers in reputable journals and conferences. She is author of 2 books. The one is Analog and Digital Communication and the other is Cognitive Radio, an Enabler of Internet of Things.
So, this session we are going to see how to modulate and demodulate frequency modulated signals. Frequency modulation, as it implies, we are going to change the frequency of the carrier signal with respect to the amplitude of the message signal. Now, the information is carried over the frequency, hence there will not be any amplitude changes. The frequency of the carrier signal would have been changed. This has many advantages in the sense we will be having uniform amplitude for the signal and the information is imbibed over the frequency of the carrier. Since the amplitude has not changed, the noise is going to affect very less. The effect of noise for the frequency modulated signal is very less. So, this is the main advantage where we have moved from analog AM modulation to angle modulation. In one of the FM is one of the angle modulation technique where the frequency of the carrier is changed with respect to the amplitude of the message signal. So, in the lab we have kits which will do frequency modulation and demodulation. What is more important while doing the experiment in the kits is we will not be troubleshooting over the electronics, we will be directly going into how the waveforms will look like and what are the readings we are going to take about. We have kit with the frequency modulation and demodulation. This part of the kit we can see as a generator, audio frequency generator. This FM modulation kit is powered by the RPS. This is the RPS power supply. This is the digital storage oscilloscope DSO, which is used to see the output waveforms. This is the AM modulator and demodulator kit. In this kit we can see the input signal which is generated by the audio frequency generator, then a frequency deviator which is nothing but the frequency modulator. This gets 2 inputs, one is from the audio frequency generator, that is your message signal, other is from the carrier. The carrier is generated inside by this kit itself and this is where we are going to provide the message. After providing the message, we can see the modulated signal out of this pin. And you have one more block, that block is for demodulation of the signal. So, first we complete the modulation of the FM signal and then we go for demodulation part of it. So, for modulation part we have to give an input signal. The input signal we have a switch here. We can generate 2 frequencies for the input signal, one is for 500 hertz, the other is 5 kilohertz. Presently the switch is at the 5 kilohertz position. So, the input signal generated is around 5 kilohertz. This input signal is to be fed in for the frequency deviator or this is a voltage controlled oscillator which will generate an oscillatory waveforms with respect to the amount of voltage that we are going to provide to its input. First we have to connect the ground. These are the ground pins which are to be connected. So, first we should provide an input, that is your modulating signal, to the frequency modulator. Now, I am connecting the ground pins using the patch cord and then I am just going to give the input. Now, before giving the input we just verify what is the frequency that is generated by the voltage control oscillator, that is the free running frequency of the voltage control oscillator. For that will be just seeing the output at the modulated signal output of the frequency deviator. Once you place the probe has 2 points, one is for the ground, other is for the signal. Once I connect the probe to the modulated signal output of the frequency deviator, this is the frequency deviator. It has 2 ports, one is for the ground, the other is for the output of the frequency deviator, where we are going to take the FM modulated output. So, at this place, without giving any input, I am just seeing what is the output produced at the output of the frequency deviator or the voltage controlled oscillator. Now, the output produced can be seen using the CRO or a digital storage oscilloscope. So, in the CRO, now the probe is connected to the output of the modulated signal output. So, after connecting the probe, you can see what is the free running frequency of the VCO in the DSO. So, this is the sine wave that is generated by the VCO. The free running frequency of the VCO is about 99 kilohertz. It is at the 99 kilohertz. So, we can measure that using the source, what type of signal we want to measure. If you want to measure the amplitude, you have to adjust the cursor and see what is the amplitude of the signal by just moving on peak to peak values. We adjust the cursor A, we are just adjusting the cursor B to see the amplitude of this signal. The amplitude will not change even after FM modulation. Cursor A is at the bottom of the peak to peak sine wave, cursor B is at the top of the peak to peak sine wave. So, the peak to peak value of the signal del Y is 2 volts, the del Y is 2 volts. We are measuring the height of the peak to peak signal. So, the del Y value is 2 volts. This is the free running frequency of the VCO. If we are going to now provide the input to the VCO, the input is provided by just feeding in the signal from the audio frequency generator to the input of the frequency deviator. Now, you can see the waxing and waning of the waveform. This waxing and waning of the waveform is the frequency modulated signal. So, depending upon the amplitude that we have given as the message signal, the amplitude, the frequency of the signal changes. So, if I increase the amplitude of my message, the frequency of deviation increases. So, this is your frequency modulated signal. So, amplitude axis, I have just adjust the amplitude, this is the time scale axis. You can see the waxing and waning of the input, and this is your FM modulated output. Just put a stop for this to see the signal properly. See the time scale, this is large, one wavelength is spaced very well here, whereas at this place it is placed very closely. As we increase the amplitude, you can see the deviation is more. This is your frequency modulated output. For each frequency modulated waveform, you need to note down what is your input signal, that is your AF signal, and the frequency modulated output signal, where you can see the waxing and waning. You can make the signal to stop and then draw the waveform as it looks like. Next step is you need to identify what is the beta of this signal. So, beta will classify the FM modulation signal as narrow band signals or wide band signals. To measure the beta and the bandwidth required to transmit the FM signals, so we have just given the input to the VCO, we have noted down the free running frequency of the VCO. As the input is provided, we have noted down the frequency modulated output waveform in time domain. We can also change the amplitude of the input signal and once again note down the FM modulated waveform. Place this is a variable knob which changes the amplitude of the input signal. So, once you change this pot to a different position, the input amplitude varies, and therefore, you can vary the FM modulated output waveform at your output. So, after viewing this, we are going to now measure what is the bandwidth required to transmit the FM signal. For that, we will be measuring the parameter called as beta. Beta is del f by Fm. So, to calculate del F, what is del F? Del F is F max minus F min by 2. F max is the maximum frequency that is created with respect to the maximum voltage that is provided to the VCO. F min is the minimum frequency that is created at the output with respect to the minimum input voltage. So, we compute beta, which is nothing but the modulation index for the FM modulated signal, as F max minus F min by 2. So, to see F max and F min, we need to view the signal in the frequency domain, which can be done using the math function. So, to see the frequencies that are generated by the FM modulated signal, we can see in the FFT mode, which is available in all DSOs. To get the FFT mode, we need to press the math knob. When you press the math knob, this fall down window comes in. So, from this fall down window, we need to select the FFT, operation FFT. Once you select the FFT operation, here you can see the FFT operation. Once it has got selected, this violet color signal is what is the FFT of the FM modulated waveform. To just see what is the FM modulated waveform, we can just focus on the FM modulated signal. This is the frequency of the FM modulated signal. So, using this, now we will be measuring what is the beta for this frequency of the FM modulated signal. To measure the beta, we are going to use the cursors, which will say what is del F. In that, we can measure either voltage or time. Now, we are going to measure, this is the frequency of the FM modulated signal. From the frequency, we need to measure what is del F. Del F is F max minus F min. So, del F, the x axis is the time domain. So, to get the F max and F min point in the frequency, you can see we can see the peak, the violet color signal going to the peak and falling down back, and rest, these are all the noise that are available in the system. So, now we are going to pick up what is the bandwidth of from here to here. You can also verify that the bandwidth occupied will change with respect to the amplitude of the input signal. So, as I increase the amplitude, the bandwidth changes. So, by varying the amplitude of the input signal, we are going to measure 2 or 3 bandwidths and write it as an observation. So, to get the beta for this type of signal, we need to adjust the cursor and get the values. So, we can have the knob at any place of your input amplitude, then get the cursors to measure as per this CRO. Now, we will be measuring cursor A. So, we can get the cursor A, we can move the cursor points, wherever we want we can place it. So, now I am going to place the cursor A, this is the point of start of the first peak. So, I am just placing the cursor A at this point, and then I am selecting cursor B. Once I select cursor B, this cursor will move anywhere we can place it. I am just moving that cursor and placing it exactly at the down, when the first peak comes down, that is at this place. Now, this will give you the del F value. Del F, according to this, 385 kilohertz. So, whatever you measure is F max minus F min. So, whatever we have got, what we want is F max minus F min by 2. So, whatever you have measured is 2 del F. So, 385 kilohertz is 2 del F. So, to get del F, 385 divided by 2. You have to take a value 385 divided by 2. So, that will be your del F. To get the beta value, you should get del F divided by Fm. For this kit, the Fm value we have set is about 5 kilohertz. So, 385 kilohertz divided by 2 into 5K. That is the beta value, 385 divided by 2 into 5K, that is 10K. So, the answer beta value is 38.5, because 2 into 5 is 10K, K and K will get cancelled. So, whatever value you got it as del f is 385. So, 385 divided by 10 is 38.5. This is the beta value for this signal. Next, you can also once again go ahead with, for this beta we will be calculating what is the bandwidth of the signal. Bandwidth BW will be equal to, we have the formula to calculate the bandwidth as 1 plus beta into Fm. 2 into 1 plus beta into Fm is the bandwidth required for transmission. This is according to Carson's rule. That is 2 into 1 plus beta. For our case, what we got as beta is 38.5. So, 1 plus beta will become 39.5. 2 into Fm will be 10K. So, 39.5 times 10K is the bandwidth required to transmit this signal. So, you can note down this as one of the observation. For the second case, you can adjust the amplitude of the input signal to any number and repeat the experiment by placing the cursors. This now the cursor is at B. So, I am just placing the cursor to the minimum most point what we got for, and then I just adjust the cursor for A. After adjusting, I just finding out what is the del f. This del 2 del f here is 455 kilohertz. This is the second reading for the second waveform. So, like that you can keep any input waveform, note down the del f value, from the del f value compute beta, from the value beta computed compute bandwidth. So, like this you can take 5 observations. This will complete your FM modulation experiment. Finally, in a nutshell, I will just repeat the steps that you have to proceed to do this experiment. To do this experiment, we need a FM modulator, demodulator kit, a digital storage oscilloscope and a power supply for it. Switch on the power supply. From the IF generator, before connecting the AF generator, note down the free running frequency of the VCO. The free running frequency what we have set is, with respect to this, was nearly 99 kilohertz. After measuring that, just give the input with some amplitude, and frequency with respect to the kit we can set 2 frequencies, one is for 500 and other is for 5K. So, we have set to 5 kilohertz and then we have given as input to the VCO. With respect to the given input, FM modulated output as produced at the output of the VCO, which has been viewed using the DSO. So, we can see both time domain and frequency domain waveform. In the time domain waveform, we just noted down how the frequency modulated waveform will look like with respect to the amplitude of the message signal. The frequency had been waxing and waning, that is your FM modulated waveform. Once you noted down the time domain waveform, then you should go in for the frequency mode of the signal, for you can find out what is the bandwidth required for transmission of this FM modulation. So, to get the bandwidth required for transmission, you have to use the math operation. In the math operation, you will be having the FFT mode. Once you select the FFT mode, we get the frequency spectra of the FM modulated signal. In the frequency spectra of the FM modulated signal, compute del f by just adjusting the cursors between the first lobe minimum 2 points. Once you keep the cursors between the 2 points, there will be a value called as 1 by del x, which will be giving you 2 del f value as 455 kilohertz. Once you got this frequency, then you have to compute in the equations as beta equal to del f by Fm. So, 455 divided by 2 into Fm is 5K. So, you can get about 10K and therefore, beta value is 45.5. Once you got your beta value, then use that beta value to compute your bandwidth. So, repeat this experiment for 2 or 3 times. This will complete your FM modulated signal waveforms. Next, we just go ahead with how to demodulate the FM modulated waveforms. With FM modulation, now we go ahead with FM demodulation. To demodulate an FM, we will be using a PLL called as phase lock loop. The PLL will create errors with respect to the difference in the phase between the input signal and a VCO output signal. If the frequency is different, equivalent to that frequency difference, an error signal will be produced. This error voltage will be taken as output. This voltage is nothing but the FM demodulated signal. So, for that usually we will be using 565, which is the PLL IC. Using the PLL IC, we can demodulate FM modulated signal. So, which has been used in this kit to demodulate the FM signal whatever we have generated. As per this kit, it is enough that if you are going to provide an input, this is the demodulator block. To the demodulator block, we are going to just provide the modulated input signal. Once we provide modulated input signal to the demodulator block, we can see the output at the demodulator circuit. So, to see the output, we are just adjusting the time scale and the voltage scale of the signal to view it properly. So, after you adjust the time scale and the voltage scale, you will be getting your demodulated output. So, we have just got the demodulated output of my input signal. So, you can see that as you adjust the knobs, the amplitude of the output signal changes. So, this is the demodulated output at the output of the PLL. Now, you are going to measure just the peak of the sine wave and you can draw the demodulated output signal. You can draw one FM modulated signal as the input to the demodulator, and the output whatever you have obtained here is a sine wave which is proportional to the message signal that you have provided to the FM modulator. You can draw this waveform as the FM demodulated output. Here also you can measure the peak to peak signals by just adjusting the cursors. This cursor A is placed over the top of the sine wave and the cursor B is placed over the bottom of the waveform. Now, you can measure what is the peak to peak voltage, that is del Y value is nearly 400 millivolts, that is the amplitude that we have provided at the input, and the frequency of this signal is nearly 4.8955 kilohertz. That is what your input frequency of, which is approximately equal to the 5 kilohertz that generated by the kit. Okay. So, this is approximately 5 kilohertz, this is the voltage signal that we have set. You can also vary the voltage signal and note down 2 or 3 output waveforms. I just increased your amplitude and then just note down the peak to peak voltage, which is about 648 millivolts. This completes your FM modulation and demodulation. Thank you.